Welcome to my channel V Concepts CHM. This is the part of the series on optical instruments where we will see about concept of eyepiece and the Ramsdens eyepiece. Why an eyepiece is needed? The magnifying power of a simple microscope can be increased by decreasing its focal length. But the focal length of a lens cannot be decreased beyond a certain limit. There is a limitation. The lens of small focal length has smaller diameter because the curvature of the surface is small and the field of view is small. Therefore, to increase the magnifying power, we will require two separate lenses which are called as objective and eyepiece. The lens near the object is called as the objective. It collects the light and brings it to focus by creating an image of the object. The eyepiece, or it is also called as ocular lens, is placed near the focal point of the objective to magnify this image. So here in this diagram we can see that the eyepiece is made up of two lenses. One is called as a field lens and the another is called as the eye lens. Eyepiece. It is an important part of the optical instrument and is used in various optical instruments such as telescope, microscope, etc. So it is a combination of the field lens and the eye lens separated by a finite distance. Such a combination is called as an eyepiece placed near the focal point of the objective to magnify the image. The eyepiece is usually close to the eye. It increases the field of view and reduces the chromatic and spherical aberration in the image. The lens nearer the eye is called as the eye lens, and the lens that enlarges the field of view is called as a field lens. It diverts the extreme peripheral rays towards the axis. As a result, they easily pass through the eye lens. Different optical instruments make use of different eyepieces. The most common eyepieces are the Ramsdens eyepiece and the Huygens eyepiece. We will see about the Ramsdens eyepiece in this video. Construction and principle. It was designed by Ramsden. It consists of two thin plano-convex lenses, L1 and L2, each of equal focal length f, placed parallel to each other, separated by a distance 2f by 3. The lenses are kept with their curved surfaces facing each other inwards. So that reduces the spherical aberration. Theory. Now in this diagram, the object and the objective is not shown. See, the object will be forming a real inverted image eye of a distant object. Now this main diagram, for your understanding, I am explaining it with the help of ray diagrams using convex lens. So this is the objective, this convex lens that is shown. It is the objective and this is the distant object, and it will form a inverted image of this object. Now this image that we have got will act as a object for the field lens. This is the field lens. This is eye, which is the image that we have got from the objective. The diagrams that have been shown here, these are ready-made diagrams. So here, even if we have got an inverted image, you have to understand that here the object is inverted for a field lens, because this object that we are getting is actually the image that is you are getting from the objective. So this will serve, this eye is now serving as an object for the field lens, and which will give rise to a virtual image I1. I1 will now serve as an object for the eye lens. Okay, so I1 is lying at the principal focus of the eye lens, so it will produce the final image. It will be formed at infinity. So these three diagrams actually makes this whole complete diagram. This objective part is not shown over here. The objective will form a inverted image of the distant object, which will serve as an object for this field lens, which will produce an image I1. This I1 is lying at the principal focus of the eye lens. So now hence it will produce the final image at infinity. We'll find the equivalent focal length of the eyepiece. Capital F denotes the focal length of the equivalent lens. So we'll write down 1 upon F is equal to 1 upon F1 plus 1 upon F2 minus D upon F1 F2. We can substitute the focal length F1 and F2. They are the focal length of the field lens and the eye lens, which is the same, that is F. D is the distance between the two lenses. 2 by 3 into F is substituted. Working out this equation, we will get 1 by F as 4 upon 3F, and hence the equivalent focal length of the eyepiece is capital F is equal to 3F upon 4. So the equivalent length of the focal length 3F by 4 must be placed behind the field lens at a distance alpha, which can be found as capital F into D upon F. Substituting capital F that we have got just now, 3F upon 4, and D is 2F upon 3, we get alpha is equal to F by 2. So that is, we have got the position of the first principal point P1 from the field lens. So that is this distance, F by 2, the distance of the first principal point P1 from this field lens, alpha is equal to F by 2. So the equivalent lens here is lying between the field lens and the eye lens. Similarly, beta, we will find the position of the second principal point P2 from the eye lens. Beta is equal to capital F into D upon small f. Substituting F as 3F upon 4 and D is 2F upon 3, we get beta is equal to minus F by 2. So that is the position of this second principal point P2 from this eye lens, F by 2. Distance of the first principal focus from the field lens, we can find out, that is the distance of this F1 from the field lens can be found as this distance is 3F upon 4 minus this F by 2 we will get, subtracting that, we'll get f by 4. Distance of the second principal focus from the eye lens, that is the distance of f2 from the eye lens, can be found as 3f by 4 minus this f by 2, that we get as f by 4. Now since the first principal focus f1 is on the positive side of the field lens, Ramsden's eyepiece is called as a positive eyepiece. So this way you can find the cardinal points of the Ramsden's eyepiece. So we'll just summarize what we have seen. The objective forms the real inverted image eye of a distant object which is not shown in the diagram at this point, which will serve as a real object for this field lens, which will give rise to a virtual image I1. I1 lies in the first principal focal plane of this eye lens. So it will serve as an object for this eye lens, and it will give a final image at infinity. Merits and demerits. Field of view is fairly wide. It is not entirely free from the chromatic aberration, since the distance between the two lenses is not equal to half the sum of their focal lengths. However, chromatic aberration is minimized by using a achromatic combination both for the field lens and the eye lens. Spherical aberration is minimized by using the two plano-convex lens, thereby spreading the deviation over 4 surfaces. So it is used practically in all the instruments where the measurements of the size of the final image are to be made. It is sometimes referred to as positive eyepiece, as it was mentioned earlier, because the real image is formed by the objective in front of the field lens, which further acts as a real object for the eye lens. Thank you for watching this video.